observing our modulator at block level, let me recall that we can write our QPSK signals. If you recall your previous lecture, we said that we can write our QPSK signal in this form: a cos of omega ct plus theta I. And this is a two-dimensional signaling scheme, and we mentioned that this can also be rewritten as a linear combination of psi1 of t and psi2 of t. There should be si of t as well. So I have to write si of t plus si2 psi2 of t. So this is actually our expression for the QPSK signal, which is a two-dimensional signaling scheme. When we saw our signal constellation, as I mentioned in my previous lecture, that you can always plot your two-dimensional signaling scheme on psi1 and psi2 axis, and the 4 points which we saw in the previous video, the 4 signal points looked like this one. So this is our constellation diagram for QPSK signaling scheme. For today, let me read out this text first, because we need to learn each and every line of this text. QPSK signal generation would be discussed before explanation of QPSK modulator at block level. So we are going to observe our modulator at block level. We'll see this modulator at block level, right? QPSK signal has 2 orthogonal carriers. So very important, keep this in mind. That our QPSK, let me magnify it a little bit so that I should be able to write over here, over this image as well. So if we observe our QPSK modulator, that is actually our QPSK modulator, as I mentioned, that it has 2 orthogonal carriers, right? It has 2 orthogonal carriers, and both the carriers are at Fc, which we just saw, that cos of 2 omega, cos of 2 pi Fc of t, and sine of 2 pi Fc t. So we have 2 orthogonal carriers, and it is shown in equation 3.22. Equation 3.22 is very similar to the one we just discussed, that it is the sum of psi1 and psi2. Each of these carriers is modulated similar to BPSK scheme, because we have sinusoid carrier, and we would adopt the same way as in BPSK scheme, which we will see shortly. The data sequence is this one, 1011. For this example, BPSK modulator, we will see that our data sequence is 1011 0001. The first bit 1 is assigned to, now this is the process how the modulation takes place at the QPSK modulator. We have to separate the odd bits and the even bits from this sequence, right? So the first bit 1, which is an odd bit, is assigned to the in-phase carrier cos of omega ct. So it is assigned to the in-phase carrier cos omega ct, which is also known as I channel or in-phase channel. So cos of omega ct is also known as I channel or in-phase channel, and it carries the first bit, or in general we would say that the odd bits will be assigned to cos carrier or I channel, and the second bit, which is 0, as you can see, the second bit is 0. The second bit, which is 0, is assigned to quadrature carrier. So it's assigned to quadrature carrier. quadrature is a sine of omega ct. If you see, well, the term quadrature means that the cos and sine, these are two carriers, carrier frequencies, and both are at a phase difference of pi by 2. They are in phase quadrature, and they have a phase difference of pi by 2 radians or 90 degrees. That is why it's quadrature phase shift key, QPSK, the name is given. So the second bit 0 is assigned to quadrature carrier, which is also known as the Q channel. It is also known as the Q channel. Hence, frequency FC carries 2 bits of information. Now, very important to note this, that if you observe your frequencies as compared to our BPSK, in BPSK our frequency FC was carrying just 1 bit in this time interval 0 to t. But now here the frequency FC carries 2 bits of information in the time interval 0 to t. So very important, our frequency now carries 2 bits of information at FC. One is at cos omega ct and the other one is sine omega ct. These two carriers, these orthogonal carriers, the I and Q channel, they carries 2 bits of information from our data. So the first 2 bits, the first bit and the second bit, is assigned to the cos carrier and the sine carrier respectively, using I and Q channel. All the odd bits are carried by I channel. So we will see that all the odd bits will be carried by I channel, and all the even bits are carried by Q channel, which is depicted in figure 3.9. So let's observe this figure now. I'll modify it a little bit. Now if we, this is figure 3.9, right? Figure 3.9. Now the things which are necessary here in this figure 3.9, I'll specify each and everything, but let me show you the first, let me show you the diagram at block level, or you will see this diagram at block level, and then I'll explain this figure to you. So let me show that diagram at block level. I'll go back to the my slides. If you move there, okay, I'll show you the diagram at block level. It's here with me. Let me show this diagram. Okay, this is my QPSK diagram, right? This is my QPSK diagram. I would like to show it here on the screen. So this is the QPSK modulator at block level. If you see what actually the QPSK signal, which is at the output here, the QPSK signal which is at the output, here you can observe this QPSK signal. Now what happens, you have the polar data. One, you have the minus and plus one. So if I say our data, if our data is 1 0 1 1 0 0 0 and so on, if this is our data, then our polar data would be 1 minus 1, then 1 1 minus 1 minus 1 minus 1 and so on. So the polar NRZ source gives you this this data, the polar data 1 and minus 1 for the bit sequence 1 0, and this is actually this polar, the odd number of bits. Now if you see over here, you have a serial to parallel converter. What does this converter? There is a serial source. We assume that our source is serial, so the input data is serial. We have to convert it into parallel in such a way that the odd number of bits are separated and they are forwarded to the through the upper branch, and the even number of bits are separated and forwarded through the lower branch. So the odd number of bits are separated, which will be, now if you observe in your sequence the odd number of bits, you have the first one, then you have the third one, right? 1, again 1, then you have a minus 1, and then you have a minus. This is the first, third, fifth, and seventh bit, and so on. So these bits would be carried by the in-phase carrier. This is an oscillator. You have an oscillator in the diagram, and this oscillator gives you an output which is a over under root 2. So this is a over under root 2 is just a scaling factor. Actually, it gives you the sinusoid cos of 2 pi fc. So it's giving you this a over under root 2 cos of 2 pi fct, a sinusoid carrier, and this multiplier multiplies the signal I of t. You will shortly see the signal I of t. It multiplies this signal with the cos carrier and forward it from in the upper branch. So this is actually a modulated carrier, the in-phase modulated carrier. Similar process happens in the lower branch, where you have the even number of bits, the even number of the polar NRZ signal for even number of bits, and Q of t. We will see Q of t shortly. It's very similar to the polar NRZ data as in BPSK. So this signal is then multiplied with the sinusoid carrier. Now, how you see you have the same oscillator. The same oscillators gives you the cosine carrier in the upper branch. In the lower branch, we have this phase shifter. This is a phase shifter which shifts the phase of the output by pi by 2, exactly pi by 2. So when you shift the phase by pi by 2 for this cos carrier, you will get minus sign, as you know that the mathematical identity that cos of theta plus pi by 2, cos of theta plus pi by 2 is cos theta cos of pi by 2, which will be 0, minus sine theta sine pi by 2, right? So sine theta sine pi by 2 would give you the phase shift. So sine of pi by 2. So this is actually a phase shifter, and then you have the a over under root 2 minus a over under root 2 is just a scaling factor. So it gives you a sinusoid carrier with the scaling factor, and you would get the cos theta cos pi by 2. So you will get minus sine of theta from here, minus sine theta sine pi by 2. So you will get minus sine of theta from here with this phase shift. So it's actually just shifting the phase, and you get this sinusoid carrier. This is multiplied with the polar NRZ signal, and this signal goes over here. Now here you have the modulated sinusoid carrier, or Q sine 2 pi fct, modulated carrier of the Q channel. Now what happens here, you have a summer which adds these two signals, and it forward it to the as a QPSK signal. Now if we come back to our modulated waveform, if we see our modulated waveform, which is this one, right? This is our figure now. Now you have the data, you have this signal now. You have this signal, which is, let me concentrate on the Q channel first, and then we will see the I channel first, and then we will see the Q channel, right? Let me concentrate on this one, the I channel, the output of the I channel. Now if you observe the output of the I channel, what do you see actually? Try to concentrate on this in this data. Now we have let me start from where I left. The first bit 1 is assigned to cos carrier. So the first bit is assigned to cos carrier. The second bit, which is in I channel, I channel, and this bit 0 is assigned to quadrature carrier, which is sine of omega c. Now, all these this information has frequency fc carries 2 bits of information. So it's clear that it carries 2 bits of information using I channel and Q channel. All the odd bits are carried by I channel, and all the even bits are carried by Q channel. So keep this in mind. Now, if you observe your data, this is actually our data was 1, 0, 1, 1, then we had 000, and then 1, 1, and 1. Suppose this is our bit sequence. This is our bit sequence. Now the polar NRZ source would give you an output for this sequence, which is given, which is shown in the next line. This is the output of polar NRZ source, right? Now we separate the in the next phase. If you see, we say that okay, this is this one is the output of polar NRZ source, and now IK. We set the set ik. This is the representation of set ik. What is set I sub k? I sub k. So this is I sub k. I sub k is actually it's a set of all the odd number of bits. So it's a set of all the odd number of bits, and you can see that the first bit comes here, right? Then the third bit comes here. Then the fifth bit. Similarly, we have the seventh bit and the ninth bit. So actually, this sequence now I of k. If I observe this sequence I of k here, now this is my sequence I of k. This sequence I of k actually represent odd number of bits from this data. So the odd number of bits from this data would give you I of t, the signal I of t, which is just a polar NRZ signal waveform. You can see this is our time axis. So now the first bit is 1, so you have a positive polarity, 1 is start. Now the next bit we are not counting. The next third bit will come after 2 bit source 2 bit period. So if you see, when the source generates this data, your I of t is the period of this signal is 2 times the period of the source data. Now the source data, if suppose the source is generating at r bits per second, suppose this is r bits per second, r bits per second, so r bps, this is how the source generates your data. So the data for I of k appears to be r over 2 bits per second, because you are taking just odd number of bits here. So in this given example, we can see that in the upper we have 8 bits while in this line we have 8 bits, while here in the second line we have just 1, 2, 3, 4, 5. We have 10 bits actually in the upper line. We have 10 bits, and here in the second line we have just 5 bits. So its data rate, if you observe, the data rate is half of the source data rate. So the first, this one, we have a positive polarity for positive 1. The next one, again the next bit is 1, so it will keep the same polarity. It will keep the same polarity for this one. So the same for the next 2 bit periods, source bit periods. And now the next bit is -1, so you would get a negative signal here. Again -1, so again negative signal here, and then you have a +1, so plus a positive signal here. This is how I of t is generated, which we discussed in BPSK scheme as well. Now what happens here, if you observe the third line, it is I of t multiplied by cos of 2 pi f ct. Familiar with this signal, cos of 2 pi f ct is this signal which is shown here. This is actually cos of 2 pi f ct. Why I say it is called, although it represents a product, but when the product is multiplied by, suppose this is plus 1, suppose this is plus 1, this level is plus 1. So when cos of 2 pi f ct is multiplied with plus 1, it would give you the same signal. So this is cos of 2 pi f ct. Now you can observe here that the frequency of this waveform is 2 Hz, because you have just 2 cycles in this period. You have 2 cycles per t. So your FC in this figure is 2 cycles per given time interval. We will observe this. We will take this as a t, right? This as a t, right? This as a t. So this point will be 2 times t. 2 times t. So in one time interval we have 2 cycles. So our FC is 2 cycles per time interval. It is 2 cycles per time interval. If let me erase it. It doesn't look good. Let me place it correctly. It's 2 over t. 2 over t. 2 cycles per. So the product I of t multiplied by cos of 2 pi f ct, I of t cos of 2 pi f ct would give you this waveform, which is represented in this first period. Now for the second period, again we are multiplying the cos waveform with the positive polarity. So again you are getting the same waveform. In the third, the cos is multiplied with a negative minus 1. So you can see this phase transition. You can see phase transition here. So the phase transition can be observed at the 2t instant, at instant 2t. After the second time interval, the phase transition can be observed, which is due to this negative polarity, the product of minus 1 and cos of 2 pi f ct, and you can see this waveform. Similarly, minus 1 with again cos of 2 pi f ct would give you this waveform, and a positive one with the cos of 2 pi f ct give you this waveform. So this is the Q of t, the in-phase channel. Sorry, this is the in-phase channel. This is the I of t cos 2 pi f ct, the modulated in-phase channel, which is exactly similar to our BPSK modulation, because we saw this type of signal when we generated a BPSK signal. So we already discussed it in previous videos. Now in a similar way, the Q of the quadrature, the Q channel or the sinusoid carrier is modulated, where we will take the even number of bits. So let me discuss that with you. Just these, we will now discuss the generation of signal for the Q of t. So if we observe your Q of t, if you see the Q of t, let me put it over the previous figure so that we can modify our signal. We can modify our signal. Okay. Now observe our Q of t. It's very similar to the one I described in that diagram there. Now for the same data, if you separate this Q, separate the odd number of bits, we would get this set Q sub k. So we get the set Q sub k from the same data. Now here I have the set Q sub k. If you see Q sub k, and this is these are the odd number of bits. Now I have the the even number of bits. Now these are the even number of bits from the above sequence. The even number of bits, you can say minus 1, then 1, minus 1, 1, and 1 again. Q of t, how Q of t is generated? Now this set qk, now if the set qk is just these bits, polar data, which represent even number of bits. We have to generate Q of t, which is the polar NRZ signal, polar non-return to zero signal. The first one is -1, so we have a negative level. Suppose this is -1, we have a negative level. The second, actually the next bit is 1, so we have a positive level, and so on. You can generate this. Now here if you see, the sinusoid is multiplied with Q of t. So a sine, as we know that the sinusoid looks like this, right? This is and so these are the two cycles of sine waveform. So if you multiply this one with -1, if you multiply these two cycles with -1, you would get this waveform in the first time interval. Here we have t, and here we have 2t, and then we have 3t, and we have 4t. So if you observe in the first time interval, a -1 is multiplied with sine 2 pi f ct, and we get a negative waveform. It is just multiplication of this waveform with -1. If you multiply it with -1, all the positive values will be negative, all the negative values will become positive, so you get this type of waveform, which is shown in the first time interval. In the second time interval, you can see it's multiplied with a 1, so you get the same waveform. No change, the same waveform, sinusoid. So we get this sinusoid in the second waveform, which is a multiplication of the 1 and sine of 2 pi f ct. Again, fc, I would mention that fc is 2 cycles per time interval in this diagram as well. And in the last part, which is this signal, it is actually the QPSK modulated signal, and it is the addition of this one, Q of t sine 2 pi f ct, and the upper signal, which I of t cos 2 pi f ct, is the addition of these two. When you add this signal with the in-phase modulated carrier, you would get this one. You would get this signal, and let's see this in another. Let me draw another figure so that we can see these signals together on a single screen. Now, if you observe this signal, on a, let me show it on a one screen. Adjust it so that all the signals are visible, because the lower one, we have to see the lower one and just the two sinusoids which we are adding. You can see these sinusoids on the screen now. I hope these are visible. Now, right? Now a little bit smaller would be better. Okay. Now, if you concentrate on this figure, you have the I of t. I of t cos 2 pi f ct and the Q of t sine 2 pi f ct, and we want to get a modulated signal, which is the sum of these two. This one minus, actually the negative of this, right? So if you see here in the expression, it's negative of this. So this is how we generate our signal. And now it should be clear why it is negative, right? Because your signal Si of t, as I mentioned earlier, that it is psi1 of t plus psi2 of t, and this psi2 is negative, right? But here we just generate a positive waveform, so we have to insert this minus sign. So we actually add this waveform with this waveform to get the modulated carrier, which is shown in the third last figure. This is actually a QPSK modulated signal. This is QPSK modulated signal. QPSK modulated signal. Signal waveform would look like this. It is suitable for transmission now over long distance. And now what happens, just concentrate on the first period. You have from I channel you have this waveform, from Q channel you have this waveform. When you add these two, you get actually the third waveform, which is shown here. And now the phase, now you can see the phase difference. The phase angle here is minus pi by 4. This is minus pi by 4, which is the result of addition of these two waveforms. So you get the phase which is minus pi by 4. Now I'll come to this one because we already have discussed this phase angle in the signal constellation diagram, and let me write it here. I'll draw my signal. Let me erase this one. Let me erase this so that we erase here so that I can draw. Let me erase it all so that I can draw my signal as well. Okay. So I'll draw my signal. If you observe our signal constellation, looks like this. See, our signal constellation looks like this figure. We have 4 signal points, right? We have 4 signal points. And these 4 signal points are actually S1, as we learned earlier, the S2, S3 and S4. We have these 4 signal points, and these 4 signal points represent the data. The S1 carries 1 1. When you have 1 1, when you encounter 1 1 in a data sequence, you need to transmit S1. When you encounter 1 0, you need to transmit S2, and for 0 0 we transmit S3, and for 0 1 we transmit S4. It was like this, I hope. So these symbols, these signal vectors, we can always draw these signal vectors which represent 4 signals, 4 QPSK signals, and you can see now the first 2 bits. If you observe the first 2 bits, you have here in this diagram, you can see you have the first waveform from the I channel and from the Q channel. The second, the Q channel, the modulated waveform sinusoid carrier. When we add this, we get this signal, and this signal has a minus pi by 4 angle. This has a minus pi by 4. Now, what actually we need to transmit? See, you have in your data sequence, you have 1 and 0. In your data sequence, you have this is for 1, this one is for 1, and this one is for 0. So when you have to transmit 1 and 0 from, because if you recall your data sequence, it was 1 0 1 1 0 0 0 0 0 0 1 and so on, right? This was your data sequence. So initially we have to transmit this 1 0. We have to transmit 1 0. So for 1 0, you can see that our signal is S2, right? No, I think I just mistakenly written these 2. So let me correct it. I hope this is not 0 1. This is not 0 1. This is actually 1. This is not. These are mistakenly written. Let me correct it. This is 1 0, and this one is 0 1. So just you can map it with your previous knowledge. You can just see your gray coding, which we did in the last class. So if you observe these signals, for 1 0 we have to transmit S4, and S4 has an angle minus pi by 4. S4 has an angle minus pi by 4, which can be observed in this. Now, the first symbol which we are transmitting, the first symbol, let me write it here. The first symbol which we are transmitting is S4. So this is actually S4. The first symbol which we are transmitting is S4 based on our data. Now, the second symbol, if you observe the second symbol, the data again here, this data is for 1 in the second period, and this data is this is also for 1, right? This is also for 1. So 1 and 1, whenever you encounter 1 and 1 data, you would transmit S1. So as it can be seen in the constellation, you would transmit this S1 signal. So S1 signal has an angle pi by 4 plus pi by 4. This one is minus pi by 4 for S4. S4 is minus pi by 4. But now we have S1. 1 and data is 1, 1. So for 1, 1, we have to transmit S1, and we can see that when we add this waveform and this waveform, the I channel and the Q channel, we get a waveform which has an angle pi by 4. Now, in a similar way, you can observe other waveforms. See this, you have a minus 1 here, a minus 1 here, or a minus 1 means a 0 here in this third period, and you have a 0 here as well. You have a 0 here as well. So whenever you transmit 0, 0, S3 should be transmitted, and you can see that S3 has minus pi by 3 phase angle. S3 has minus pi by 3. So this phase is minus 3 pi by 4. Sorry, not minus pi by 3. It is minus 3 pi by 4. Minus 3 pi by 4. So this angle is minus 3 pi by 4. This one in the constellation diagram, you can observe that this angle is minus 3 pi by 4. And you are getting here, so we have S4, then S1, and then we are transmitting S3. This is the symbol S3, which can be seen in the constellation, signal constellation diagram, and it is the waveform is given here. In the fourth period, you have a minus 1, you have 0 again, a 0 here, and we have a 1 here in the fourth period. So when you add these two, you get this waveform, and this is a waveform for the angle for S2, because you have a 0 and a 1, and you can see 0 and 1 when we transmit a 0 and a 1, we actually are transmitting S2 in our constellation diagram. So in our constellation, S2 is at an angle of this angle, which is 3 pi by 4, which is 3 pi by 4. So this is actually our S2. And in the last symbol, which is 1 here and 1 here, again 1, 1. So we are transmitting S1, which is at an angle of pi by 4, which we saw. So this is how this modulation, QPSK signal modulator would generate the signals. This is a QPSK modulated signal which is generated, and you are actually transmitting S4, S1, then S3, then S2, and then S1. This is the sequence. This is the sequence of symbol which are transmitted from source to destination. Now let me clarify this diagram. Let me show you the other figure which we actually you are observing this one. Let's see. This this is how you generate the QPSK modulated signal. Now the signal I of t and Q of t, if you observe I of t and Q of t, the expression for I of t and Q of t is given in this form, which is which can be observed in equation 3.25. So your signal for I of t is, the expression for I of t is given in 3.25. Now what actually this 3.25 gives you is very important to note down, because this notation you should be very clear about this notation. And let me write it for you, because we have to we need. This is I of t, and it is the expression for I of t is a summation for all I with sub capital I with sub I, and then you have p of t minus I. Now what does this summation means? Let's try to understand this summation, because it represents mathematically I of t. We just saw this a very simple signal. So what this complex summation, usually sometimes students are confused to observe these kind of complex expression. So don't worry, don't be afraid from this expression. If you observe it, this is just, it's very simple. Let me give values to this I, and you would it would be very clear to you. Now if you recall, first of all let me draw P of t. If you recall your P of t, it's a pulse, just a very simple pulse, a very basic pulse, and we said that it's a pulse from 0 to capital T and this interval. So this is a pulse, simple pulse, positive 1 with a positive 1, 0 to t. And if you recall your the knowledge of your signals, this notation P of t minus capital T, it would be just a delayed version of this pulse. It would be a delayed version of this pulse. So if you delay this by one time interval from t to 2t, so you get this P of t minus. Now what this I means, I is just integer, right? From 0 to it can be 0, it can be 1, it can be 2, and so on. It takes these values. So for all I means, for all the integer values we need this summation. So if you add this, for let me put some specific values of I, and then we try to solve this equation. We try to see our signal. So for some specific value of I, suppose my I is just 0, 1, 2. So this is summation I of t. I of t would be summation for all I means, for all I 0 to 2. So the summation would be this one, P of t minus I t. Now if I open this summation, how it would look like? It would be I naught P of t plus I1 P of t minus capital T plus I2 P of t minus 2t, right? Minus 2 times capital T. So the expression would look like this. We have three terms now here, and we already mentioned what this I0, I1 and I2 are. This is actually the data, data from set Ik, as this is actually the set Ik. We already saw it in the figure, and these were the odd number of bits. So we had I0, we had 1, this set was 1, and the second one was also 1, and the third one I expected it was 1, 0, 1 1 0, yeah, it was -1 and so on. So just I am taking just three of them, I naught, I1 and I2. So this is my I naught, this is my I naught, the first one is I naught, the second one is I1, and the third one is I2. So just taking these three, and we would like to show our expression and the signal. We will compare it with our signal, that how our signal is represented by this summation. Now observing the signal, I1 is 1, right? So you have P of t. You have P of t. I naught is 1, so you have P of t. Similarly, I1 is I1 in this expression is 1, and P of t minus, so 1 times P of t minus t, so you have P of t minus capital T, and then you have a minus 1 times P of minus, not plus here, so let me erase this one, this is not plus, it's a minus sign. We have a minus sign P of t minus 2t. So this is what we are left with that expression I of t, right? Just for three terms. Now P of t, we know this is a pulse which is from 0 to t. P of t minus t is a delayed version of that pulse. So if you want to draw these, you can draw it like this, because you have now three waveforms which are added. So keep this in mind. What actually you have three waveforms. Let me draw it specifically. You have three waveforms. The first one is from 0 to t plus 1. This is P of t. Another one is another one which you have to exist in the time interval from t to 2t, right? T2 from t to 2t. Again, it is a positive pulse, and the next one which exists, which you have to add, is actually minus P of t. So it's a delayed version, but it, at the same time it is multiplied with minus 1. So the pulse is multiplied with minus 1. So it's actually minus P of t minus 2t to 3t. It exists from 2t to 3t. So if you add these two, you will get your I of t, the first, and the I of t can be represented here on this line. So it's a positive 1 up to t. Again, this one, it is because of this one. When you add this one from t to 2t, so from t to 2 times t, again you have 1, and from 2t to 3 times t, from 2t to 3 times t, you have a minus 1. So your waveforms looks like this. I of t, it's 1, and then you have a minus 1. In the first three, I naught, I1 and I2, I just took this here I of t, which is shown in the above figure. You can draw it for other bits, and you should be able to understand this notation, which is the notation of actually this I of t, the summation notation. You can use it, and it should be clear. This notation should be clear. The same notation is used for Q of t. So if you see your Q of t, it is the same notation is used for Q of t. Let me specifically write it for you. If you observe your Q of t, the equation 3.26 is the notation for Q of t. Now, so the notation for Q of t and I of t should be clear. I hope you should not afraid from these summation notations right now, because you can always, you just see your Q sub k, which is a set of odd number of bits, even number of bits. This is a set of even number of bits, and you can form your Q of t from just addition of these delayed version of P of t. So I hope this is we covered whatever the QPSK modulator, and we would leave the demodulator for the next lecture. You are always welcome to ask any queries if you have. So you can just send me the queries if you do not understand, or if you compare it with your book and you find some conflict. So just let me know, and we will try to resolve that conflict, because we are not going to leave any conflict in the theory